So I'm going to talk about HARES, the Hardened Anti-Reverse Engineering System, known by some as the security silver bullet. So I work for a small company called AIS in Denver, and I do lots of low-level security research, so play in SMM, VMM, kernel space. That's all the fun stuff in my opinion. So real quick, before you all fall asleep or leave to go get, jumpstart the line for the beer, basically what HARES does, it allows you to execute a fully encrypted binary. So you can take a PE application, encrypt it with AES, and then run it seamless to the end user. The performance impact is quite minimal. We're seeing about 2% CPU overhead on the new unmodified Intel Core series. And so this is not a new architecture. This is not a hardware modification. This is you go out and you buy a computer and then you run an encrypted program on it. It prevents the key, the decryption key, and any decrypted instructions to leak outside to even a compromised operating system. So if someone has found a way to get kernel privileges, they'd still be unable to recover those decrypted instructions. And it works on unmodified binary. So this is not a source level kind of obfuscation technique. This is taking an existing binary and then protecting it. So application code can be used to develop attacks. I think this conference is a pretty good testament to that. You can run it, software through a fuzzer, find a crash case, and then be able to kind of go from that and massage that into a much more lethal type of attack. Algorithms that might be sensitive are exposed to copying or theft, or you can write a keygen for a software, or you could steal it in that way. And then also code can be reused for unintended purposes. So there was a great talk by Mudge showing kind of the size of defensive software that is now upwards of 10 million lines of code, which is like the perfect playground for people who want to mine that for ROP gadgets. So this makes it much more difficult to mine for ROP gadgets because you're not actually sure what the underlying instructions are. So there's a couple things out there right now. So there's obfuscation and packers. I'm sure everyone who does malware analysis is very familiar with kind of what's out there. Though a lot of analysis and tools and live debugging, you can recover the instructions. It might be much more annoying, and they might have little tricks that be able to make it very unpleasant, but generally the CPU still needs to run the instruction. VM-based obfuscation is kind of it creates like a randomized instruction set which is mapped through a virtual machine. It can impact performance because it's not running natively, maybe just in time or interpreted. And then also you still have to kind of map it at some point. And so if you have, say, a kernel level debugger, you'll be able to kind of reverse that mapping to some degree. Again, it's going to be very unpleasant, and you're probably not going to want to do it, but it's possible. And then there's the encrypting the entire operating system with trusted boot and full disk encryption. That prevents offline attacks, but once the system is loaded, it's still kind of fair game. All right, so a little bit of background first. So AES&I is an instruction set that they added on top of the Intel CPUs. Basically, there was some software-based caching attacks against AES that were able to kind of weaken the implementation. And so also they have some performance impact. And so these are instructions which allow you to do AES on the CPU with hardware acceleration. The hardware logic is faster and more protected against kind of these side channels. Supports 128-bit or 256-bit AES. It just provides the primitive. So you still need to do smart crypto on top of that. So you could, by default, do electronic code book, and you'd still have kind of an insecure product. It doesn't magically make your software secure. It's just a good kind of building blocks. Trezor took AES&I as a set of Linux kernel patches, and then put the AES key into the CPU debug registers, which then it blocked in kernel space to provide accelerated and cold RAM resistant AES on Linux. So it created a new Linux crypto capability that did faster and more resilient AES support. And then the key was loaded at early boot, so maybe in single user mode or one of the earlier init levels where there might be less applications running and less likely that you have a browser open which is going to go to a malicious payload. So basically that was for data, and then this work will extend that to execution capability. And how it does that is through a technique called TLB splitting, which I'm sure many of you have heard of. So basically the TLB, the translation look-aside buffer, is a cache that kind of maps and saves the translations between a virtual address and a physical address. So operating systems can manage applications' view of memory by using paging, and the architecture supports that by using page tables, and kind of you can set up the container for memory, and then the application can kind of run without having the operating system have to step in at every juncture. However, every time you walk these paging structures, you incur a pretty significant performance hit. I think it's possible to set up maybe 7 lookups for each possible one-page lookup. So you have to hit memory 7 or 8 times just to read 1 byte. So very slow, so they added this cache, the TLB, which improves performance significantly. And logically is treated as a single entity. It just caches virtual to physical addresses. This is the neat part. So physically, it's actually multiple components. On the CPU, they separated it out into 2 components. One that's closer to the data fetch logic, and one that's closer to the instruction fetch logic, so that you get some minuscule performance benefits, but since it's being used pretty much at every instruction, that benefit will actually have some real impact over the lifespan of the CPU. So with the split TLB, you're switching your x86 platform, which is apparently a von Neumann, so you have a single shared and identical data and instruction bus. So if you were to, antivirus, you were to read a page of memory and verify that there was no malware there, and you said, okay, this looks good, and when you're actually executing it, you're going to run what you just read. And it turns that into a Harvard architecture, which is one with separate data and instruction buses. And so this was used by the PAX guys, GR Security, to emulate the no execute bit back before that existed in hardware. And then it was used in Shadow Walker to do a memory hiding rootkit. So they would put a rootkit into kernel space, and then they would use TLB splitting to redirect any data reads to the benign, regular kernel module. But if you were actually, they get that kernel module scheduled, when the CPU executed code at that page, it would then run the malicious payload or whatever routine was doing. So normal operation, which I would say is like close to 100% of the time, you're going to have a data read and instruction read. They go through the data or the instruction TLBs respectively, and they're going to go to the same region in physical memory. As you can see with the split TLB, they go different places. And so you don't have a consistent view of memory in a Harvard architecture. Some systems are built like this specifically. So AVR is an example of that, where if you have a pointer, you can either point and you treat it as data, it will go to one place, whereas you treat it as code, it will go somewhere else. This was really the thorn in my side when I did some of this work, the STLB. So they've added a larger L2 cache between that. I'm not sure if you can see it, but in red is the STLB, and there are bi-directional arrows on this block diagram from the Intel software developer manuals between the instruction TLB and the data TLB. And so the issue with this is now you no longer can maintain that split in between, because if something gets evicted from, say, the ITLB, but it's in the DTLB, is also in the STLB, the instruction, rather than having instruction TLB miss, rather than having to rewalk the page tables, it'll just grab it from the STLB or the DTLB. So that kind of broke the split TLB architecture when they came out with the Core I series on the Halem and newer. So that's where I started working for a DARPA cyber fast track program. And I didn't actually know they'd done that until after I already had got the program and started working on using TLB splitting for program verification. We were looking at some applications that had data and code interleaved, and we wanted to be able to repeatedly measure software so we could run a hash on a program that might be changing in kind of a sub-page boundary, and to make sure that if something was changing, it was because of a code injection attack, not because of the variables gaining natural state. So we had to find a way around this STLB, and luckily we have extended page tables, which is an Intel VTX extension, which allows you to set up page tables for a VMM or a hypervisor to manage operating systems memory, just like an operating system can manage application's memory. And so you can create the same or very similar paging structures for each VM, and then the hardware kind of handles all of the translation automatically from what they call a guest virtual guest physical address to a machine physical address. And then so I created a thin VMM that kind of simulated Harvard architecture on a per process basis. So this kind of had a VMM component and a Windows kernel driver that could introspect into process creation and the internal Windows settings. So it's Windows 7 kernel driver. It was based on the VM CPU rootkit example. It doesn't provide any emulation of devices, and the OS retains direct control over the hardware. So this is not a virtualization platform that you would use to run multiple OSs. This is just to get up in that very privileged space to be able to use some of these new features. And the performance impact is very minimal, 1 or 2%, depending on what you're doing, how much you're introspecting. And then you can use VMCS, the virtual machine control structures, to track architectural events. So you can set exits on some pretty scary stuff. One example is you can have it trapped to the VMM whenever they use the hardware cryptographic random number generator. So if you call the rand instruction, which should give you a very strong random number generator or random number, you can actually trap to the hypervisor and then put whatever information you want into that return. So then I took this VMM with HARES and I hoisted basically the same effect, the Trezor on CPU AES code into the VMM. So now we were doing on CPU AES from the VMM perspective. And so we added an exit condition for any debug register reads or writes that would get either silently blocked if it was a write or just would return null. So that way the key, even to a compromised OS, trying to read the debug registers would never be able to kind of recover that information. And then we decrypt executable sections of program into execute-only memory. And I'll talk about that a little bit more in a second. Then that's happening right now kind of in the background. Then on the Windows kernel side, we just register a callback for process creation. As soon as a program that's been encrypted runs, so what we're encrypting is just the executable section. So it still has a valid PE header, still has unencrypted data. So it's loaded like the Windows, any other Windows application. It's just that if you were to actually let it run, that first instruction would probably be garbage and it would crash. So we actually get notified after the program is loaded into memory, but before it's been executed. We then parse the PE and identify which regions are executable and probably encrypted, and then we pass all that in a hypercall to the VMM saying, here are the sections that need to be protected and decrypted into execute only memory, and then also when the program quits, we get notified as well saying, please wipe this from memory, do the teardown of the TLB split. So now that we're running the program, we're doing TLB splitting. So if a data fetch is received by the CPU, even from the application itself, so if you find a memory disclosure bug that's targeting and you're going to use it to look at the source code, that'll actually get redirected to the encrypted data copy as well. And then it's directed by this EPT, so it's hardware enforced kind of TLB. So the internal to the CPU, it can kind of know the intent of that memory fetch, and if it's a data fetch, it goes to the encrypted copy, and if it's an instruction fetch, does it go to the decrypted version. And then we have a couple other little things that we need to worry about, like Windows moves applications around, and then make sure that our structures correspond with the ones kind of at the EPT level and at the kernel level. So we have a couple test cases, mostly like calculation of pi was it's purposely inefficient to test CPU time, so you run it for a long time, and I'll show you in a little bit in the demo, just to see how much the CPU was impacted. Random sort is like the worst sorting algorithm ever, and it just does that to test randomized memory access across different cache lines to see if that also has a significant performance. Coin flip calls a lot of different shared libraries and random number generators just to make sure that, even if we had an encrypted application but a decrypted library, everything would still work. And then timers monitors performance impact as a ratio of cycles to your wall time. So I'm not sure if you can see this, but the slides will be distributed later. On average, it's about 2% performance hit. There is the second one, the randomized sort, which has a 95.83% performance hit. That's actually due to just the slightly longer startup time. So the randomized sort took 0.01 seconds, and it took 0.03 seconds. But even if we turned off TLB splitting, just had the Windows process be called and do, say, yes, continue, without doing any on a completely decrypted application, it still had the same performance hit. So we're kind of lumping that into a constant increase of 0.015 seconds for each test case, which is why that percentage is so skewed, even though the overall performance impact is pretty small. And then also, we wanted to make sure that it would work on a software that we didn't have source code to. So we don't work for Windows or Microsoft, so we don't have access to Notepad, Paint, Calculator. And we also wanted just to test the usability of these applications to make sure that it wasn't unresponsive or too difficult or too slow to use in a realistic use case. Oh, and it wasn't noticeable. It was like running Calculator, which is not a very highly intense process. Maybe if you're playing Crisis, it would be more impacted, but you could still calculate numbers, so that worked. So the demonstration system, which I have some videos for, there's a couple lazy engineering limitations. So it has to be AES Core I series with the AES&I. It's a Windows 32-bit 7 OS right now. We have to use single processor for the time being just because the VM CPU only supports one, but you could actually have a per core key, so you could have multiple differently encrypted applications running on the same system as long as they were pinned to the proper core. And the 2 gigabytes of RAM is the most frustrating one, mostly because the Windows kernel changes how they do paging and Windows memory layout if you have more than 2 gigabytes. And we had hard-coded a couple values, and so rather than change all of that, we just said, all right, we'll just truncate memory to 2 gigs. And then we turned off PAE because we didn't want to write PAE memory manager, which would be very unpleasant. Okay. Cool, that didn't work. Okay, so this is a video, and I'm going to stop through as we go through. This system is a Core 2, so it doesn't have AES&I, and the one that it does is very heavy, and I didn't want to bring it. And all it shows is a program running, so it's not the most exciting demo. If you want to look at it closer where the resolution is enough to actually read what's on the screen, come find me during the break or anytime during the rest. So this is without HARES. So we're running our, it's calculating pi. It's getting more and more correct on the right side. We attach to the process an IDA. And then we're going to go to the entry point, and you're going to see a bunch of different kind of setup calls in the text section here. So I personally don't really know how to use IDA, so if you laugh because I'm like going through menus or whatnot, it's just because I don't really know what I'm doing. So you can look here, and you can trust or you can verify later that the disassembled code is valid for the start of a program. Yeah, IDA's pretty happy. Okay, now we're doing the same thing, but we've taken the EXE and we've run it through a tool which just encrypts it with the PE sections. that are marked as executable. And so now it's running again. We're going to perform the exact same process. We go back to the same address and memory of where the entry point is. So the code here, I can't even read it. So it's very poor resolution, but it's nonsense. It's like doing all sorts of weird non-setup things. And you'll see I have another video at the very end, if there's time, that shows like it's returning from NTDLL, and the calling instruction was the letter Y, the ASCII value of Y. And IDA just said, you know, you just jumped to the middle of an instruction that was partially ASCII text. What are you doing? So I'll show you that later if there's time. But the program still runs just fine. So it's kind of seamless to the user, the end user, who might not know this is happening, that's going on. So what did I do? Okay. So there are a couple challenges from the engineering side, which I think are the least interesting, so I'm going to go through them pretty quickly. So a lot of applications, when they're compiled, they actually compress sections down. So rather than having an entire page just for code and just for data, they'll just fit them down to the smallest number of pages possible. And so in this instance, you'll have strings that are like right next to the function that uses them if they're passing like a GUI function or whatnot to start drawing stuff on the screen. Because the application itself can't even read the decrypted data, what it's going to do is it's going to get like junk. And so you'll try to, on the calculator, we'll put the little clear all, or that text says clear, but instead it's going to be like nonsense, garbage, AES, and there's probably not going to be a null terminator, so it's just going to run for a very long time and like crash the program. So we had to figure out a way around that. Applications in user space get paged in and out as the operating system might need to free up memory, and the application might not be actively used, and will page things to disk. That's a problem for us because it might get paged back in somewhere else in physical memory, and so we need to update all of our mappings. And then Windows itself will relocate applications and perform copy and write to reduce the memory impact if you're running multiple instances of the same application. So the mixed code and data was the hardest one. I think this is the one that was the most interesting research to go forward. There's some easily identifiable stuff. Like there's a lot of stuff that's been published, and there's actual tables. That's like, we just parse those out and we just leave those as data. We don't encrypt those. The strings that you're put in that are kind of injected into the code, that's the really tricky part. If you have the source available, you can just tell your compiler not to do that. Only have a binary, you could manually reverse engineer it, which is not very feasible. If you have debug symbols, you're set. And then what we had to do for a lot of these applications, like Notepad, was we have a provisioning and learning mode. So you run the application, you kind of exercise a little bit, and then it will actually track. It does a split TLB, but just to track memory locations on an unencrypted binary. And then it kind of creates a mask of areas to not encrypt. And so this is, you would assume it would be running in a place, the trusted system, kind of before it's deployed to a hostile environment. And so for the proof of concept, it works pretty well, but it's pretty unreliable as that scales up, as there's more and more to exercise. We lock the pages into NonPage Pool right now, just so that we don't have to deal with that, which is very limited, especially if you already limit memory to 2 gigs. And then we VM exit on every process change, so we can rewalk the page tables to see if the application has been moved around, and then update. We have another hyper call to update our mapped pages. All right, so security benefits. Everything. Protects everything. Hackers are done, according to some sources. It makes reverse engineering more difficult. It protects against kind of the weaponization going from a crash case to a remote code exploit. Mining application for gadgets. And then also the Harvard architecture is naturally resistant to code injection attack. if you do some like Windows API call that might push code over another application, all of that is going to get transparently rewritten over the data section, which will never get executed. So it's kind of provides that extra benefit just from being from the Harvard, using the Harvard architecture. So weaknesses. There's a lot of hardware level weaknesses. So if you have a JTAG, an XDM, or an ICE, which are somewhere in the tens of thousands, but they have a new one from Intel that's like about $1,000. It sits in between the CPU and the motherboard. With that, you'll be able to boot the system and just pull the keys out of the debug register. Memory dumping currently, if you do cold RAM attack or other type of memory dumping, that's going to be able to recover the decrypted instructions in memory, and it's going to be just like the PE file, so you'll be able to see it, and you won't have to do any fancy, slicing or carving. But the key will still be protected. DMA, that was an attack against Trezor Hunt. That we can protect using VTD, which is another extension of the virtualization that allows you to set up basically paging structures or an IO MMU against DMA attacks, so we can actually protect those regions from being written to or read from by devices directly. Side channels, I'm sure there are tons. There's some crazy side channels that I've seen with heat and power and cache, so I'm sure that that's very much possible. And then emulation or VMM. If you could run this in a nested hypervisor or on a very well-made emulator, you'd be able to kind of do some more reversing, just pull the debug registers out. So how do we get past this? I already mentioned VTD. Cache as RAM is a technique used by Core Boot or Core BIOS, whatever they're called themselves now, which allows you to execute from cache only, and it's never written back out to RAM. So you can persist memory pages in the CPU cache, which these days are maybe like a couple megabytes all the way up to tens of megabytes. So if you had a very sensitive application, you'd be able to, or perhaps portions thereof, you'd be able to keep them locked only on the CPU, and even a cold RAM attack or some type of memory bus snooping would not be able to recover those decrypted instructions. How you launch it, so the AES NI Trezor just did it early on boot, but I think that that's a little bit naive in the sense that there's a lot more terrible attacks, and so especially if you have a malicious hypervisor. So what I would advise is using a trusted launch. So Intel TXT, you could launch a measured launch environment, which is run by a special mode of the CPU, and make sure that there's no other hypervisor there, and then the key would be stored in the TPM and only unlocked if the environment matched a certain policy. That can also be done from software as well. There's some work out there. One of them is called Conqueror, which does this using timing-based attestation, and you can do it from software, and you can make sure there's no VMM or emulation or live debugging. I think also it'd be really cool to combine this with unique compilation. So there's some new work out there that takes a program when you have source and it compiles it into a randomized layout for each time. So now you have a very unique application, and it's very hard to kind of introspect and to see what that program is doing. And so now you're going to have a program that maybe if you find an exploit for, it'll only work for that particular instance, not for the application kind of in general. So unintended use cases. So this was originally designed as kind of a defensive, good, warm, and fuzzy program, but it was pointed out by some folks that that might actually not be its only use case. So a couple points to that. So key management becomes much more difficult in the offensive environment, where you're not going to be able to go and put hands on a system and put a key into the TPM and set up TXT and be able to maybe educate your users if something happens. And so it's a little bit less studied. And I think that a little bit more challenging, especially if someone's looking for it. They might be able to capture that initial load of the key either into the debug registers if the hypervisor is not set up, or the push down to the system. So that's a little bit more challenging. So I think it's a little bit easier to use defensively when kind of everyone's clued in than offensively, but it's certainly something to note. So I was telling this to the next speaker, actually, and she thought that, well, heuristics on AV, we'll see that the entropy of these programs is very different because they're not necessarily valid instructions, and so it might think, oh, this is very suspicious, it's probably a packed binary. So I ran it through VirusTotal. I took notepad.exe from Windows 7, the same one that I ran encrypted, and I uploaded it to VirusTotal, and sure enough, 4 out of 57 AVs, I think AVG is the only one that I ever heard of, but marked it as suspicious. And mostly you can see that it's either packed or it's based on heuristic, just by the little result names. And just to get some ground truth, I took the unencrypted notepad.exe, uploaded it to VirusTotal, and sure enough, no AVs flagged it as malicious. But it also said, this is the MD5 sum of the one that's published by Microsoft, so it's been whitelisted. So I went in and I found like a string somewhere in there that was like in the preamble of the header. I changed 1 bit. I re-uploaded it to VirusTotal, and now, again, 4 out of 57 AVs thought that Notepad was unencrypted, was malicious. So I guess the moral of the story is that I don't know what AVs actually do, but cool. So I guess some concluding remarks. It kind of demonstrates the viability of this. Intel's SGX is coming out, which is kind of like this, but with hardware augmentation. So that is going to basically, I think, move this into something that you might actually be able to use and see in real life. And it's going to substantially increase the security. When you're doing this, this is more for legacy use. It makes reversing much more difficult with minimal performance hit. And then you can provide some legacy systems, maybe some breathing rooms, until the appropriate fixes can be implemented. And as I said, yeah, SGX I think is really cool, and I'd like to get my hands on it and play with it and see how it compares and what it can do that HARES doesn't from a reverse engineering standpoint. I wonder if they can maybe turn off the JTAG chain when you're in SGX mode so that you can't even use a hardware debugger. So thank these guys for their help or support or input. There's a lot of references. I'm uploading a 11-page white paper with like 17 references and figures and diagrams and background information. See you at next year, SyScan'15.
Say, taking your encrypted notepad.exe as an example, where's the AES key, and can't I just write an unpacker to then reverse the unencrypted version?
Can you repeat the question?
Just about the key management, like if you produce an encrypted notepad.exe, where is the AES key loaded from into the CPU in the first place?
So when you're actually encrypting it the first time, when you have a clean notepad and you want to deploy one?
Well, when I want to execute the encrypted version, where does the CPU load the AES key from?
Okay, so I touched upon that a little bit. So you could use a number of different key management and key deployment techniques. The one I would advise would be using something like Intel's TXT, so you can make sure that you're the only software running on the system. You can measure according to your launch control policy, and then the TPM can be sealed and have it so that only when the system is in that state and the hypervisor is loaded, it'll load it specifically into the debug registers, and then the hypervisor can block access to it. So this could happen at very early boot, or it could happen kind of in situ. There's a tool out there called Flickr that allows you to run verified code in situ with the operating system. So yeah, the key loading is the challenge. TXT is not fully out there, and every system is usually the business class. But as I said, there's also techniques like Conqueror that allow you to do that same verification to make sure that you're not being monitored by introspective hypervisor or a malicious debugger from software only. So good question. It's just there's a couple different answers to that depending on what your paranoia level is, but I would advise TXT.
So basically it's dependent on distributing the keys separately and loading it separately, not as part of the same binary, obviously.
Yes, that's correct. They're kind of offline. So in an enterprise deployment, I could see this as having an HSM and an app store of types that each CPU has a key that when it's kind of provisioned and installed, it has a unique key that's also stored in the HSM. And then if you go down to your desktop and you want to run a new program, click on it and it takes the application, runs it through the HSM, and now you have a completely new, apparently new, binary that's only will work on that system. So if you try to steal it and take it home or whatever and to do more analysis, it will just die when you remove it.
Anyone else? I have a question. Assuming we do what you say, how long you think it would take the Chinese to overcome everything?
Well, I mean, this doesn't also, I didn't mention, but SMM attacks, right now, this is vulnerable to. So I have some future work that I mentioned in the white paper about detecting rogue SMM. One of my coworkers just did his PhD dissertation, and he can do cache level analysis to detect SMM tampering. And so you'd be able to at least detect if there's a malicious SMM. But until we have like an STM that's been published and verified, it's still going to be vulnerable to SMM, and then obviously supply chain attacks as well.
Okay. Oh, okay.
Would you be able to push patches to a machine running this?
Did you get that?
Yeah.
Yeah.
I think if like a case splice type patch or a file-based patch.
Yeah.
Yeah. So AES at the block level, and using a kind of a modified counter mode based on the kind of the virtual or the RVA, if you could calculate the diffs using the same key and the same IV, you would be able to kind of identify the differences and apply those to an encrypted binary.
Anyone
I also
else?
forgot to mention, this works on PE files in general, not just applications. So kernel modules as well are PE files, and this similar approach would work as well.
Okay.
Yeah, should there be a rogue SMM, couldn't that patch out the check for the rogue SMM?
SMM is much more difficult to use as an introspective capability. It doesn't have the same nice features for exit conditions like VMM does. If it could detect what was going to happen enough times, so really the only thing you're going to have is it gets interrupts from certain events, which you can set on the MCH. But probably the most prevalent one would be a periodic interrupt. And so if you can do the check in between that period, then you'd be able to at least detect its presence. I don't think you'd be able to fight through and protect against a rogue SMM, but you'd at least be able to detect its presence there. If you have an STM, if you run with TXT, then you'll be able to be very sure that you'd have no rogue SMM.
How do you handle relocations in PE files?
Ah, great question. Yeah, so obviously Windows, after we finish, will actually go through and like relocate, but it's relocating the incorrect. So we basically rewrote our own that undoes their relocations by parsing the PE, and then once it's into the execute-only memory, we'll go and redo the relocation. So we wrote our own partial loader for that. Yeah.
Thank you.
Okay. No questions? Thank you, Jacob. Good job. That's awesome.